guys, and welcome back to another video on the channel. In today's video we're going to be looking at another example, finding the total work in a given vector field using Green's theorem. So consider the following vector field, so f of x and y, and the x component is x and the y component is negative x squared y squared of j. Okay, and we want to find the total work done in this particular region C. So we write out this little expression here, which pretty much tells us we want the total work of the vector field in some given contour C. So the contour is the closed region, so our closed region in this case here will be this here. So it goes from 0, 0 up to the point 1, 1 over to this way to 0, 1 and then down finally back to here. So this is the closed region here. So if it's a closed region, we use a contour integral, and because of this specific thing of the orientation, we can use Green's theorem. So Green's theorem says that the contour integral of our path C of our vector field is going to be equal to the integral, well, the contour integral of C of the x component. So this oh, that's meant to be a highlighter. This P represents the x component of our vector field, plus Q, which is our y component of our vector field. So that would be this bit here. And that's equal to the double integral of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y of dA. Now dA just represents dx dy, okay? And then we'll sort out our bounds really quickly. Now, if the vector field is conservative, this term is 0. Because if a vector field is conservative, that means the work done will be independent of the path. But we can double check if it is conservative or not. So what we can do is find what the partial derivative of q with respect to x is. So what we do is differentiate that with respect to x, okay? So we have x. So that term is just going to be 1. Okay. Now we differentiate this with respect to y. Actually, no, I've got it the wrong way. Sorry. You differentiate this term with respect to x. So dq dx is equal to, oh sorry, pen's playing up a bit, partial derivative of all this. Sorry, I nearly mixed up the terms there. So you treat y as a constant because it's a partial derivative with respect to x. So you have this, move the 2 down the front, so we have negative 2xy squared. Okay. Now to find out what dp dy is, differentiate this entire thing with respect to y. So we'll have d with respect to y of x, and that whole thing's going to be 0. Now we can see dp dy isn't equal to dq dx, so the vector field is not conservative. Hence, the path will matter and will determine the work. Okay. So let's try and work out our bounds of integration. So in our previous example, we had single numbers for x and y, but we can see. Let's just take a look at x in this case here. X goes from 0 to 1. Okay, so 0 and 1, that's where x belongs. However, y is a bit more complex. Y is going from 0 to 1, but it's on an angle here. So it's actually going from x to 1, pretty much. Okay? Because that is pretty much the path of y, because it's going on an angle. So when our double integral is set up, so if you want the total work done, oh, that's not work, that's force, of force dot integral, our bounds for x are going to be 0 and 1, but our bounds for y are going to be x and 1. And now you can work that out because you can work out the equation of this line here using just basic rise over run and stuff, and you'll see that that is just y equals x, pretty much, and it only goes up to 1. So the bounds for y is from x to 1. So when we set up our double integral, we're going to do x on the outside, so 0 to 1, and then we're going to go x and 1 here, and then we'll have the partial derivative of this, so negative 2xy squared. Oh, that's true, it's a constant, that's 0, sorry. No, I got that wrong. Minus 0. dy dx, okay? So, all we have is just a double integral from 0 to 1 of x1 of this expression here. So, when evaluating a double integral, treat the other variable as a constant. So when we're integrating with respect to y, we're ignoring the negative 2x. So, add 1 to the power, divide by the new power, so we'll have negative 2x y cubed on 3 from x to 1 of that. That's our inside integral, and then we have this outside integral still here. Okay? Substituting in the 1, and then you substitute in the x. So you'll have negative 2x of 1 cubed on 3 minus 2 on x, now x cubed on 3. Okay? And this is all inside the integral now. Okay? Go down a bit, if we let go, and we'll simplify this a bit more. So 0 to 1, this here is just going to be negative 2x on 3. This here is going to turn to a positive because of negative and negative, so you have plus, and then you have 2x to the 4 on 3 dx. Integrating all these, add 1 to the power, divide by new power, so we'll have, what's it called? 2x to the 5 on 5 times by 3, plus negative 2x squared on 3 times by 2. I can cancel those 2's if I wanted to. And I still have these bounds here we got to plug in. So we'll have 2x to the 5 on 15 minus x squared on 3, 0 to 1. Plug in the 1 because the 0 is just going to be 0 anyway, so your work will be 1 plugged in there minus 1 plugged in there. And that should give you, I'll plug it into my calculator because I'm going to be a bit lazy. So I'll go 2 on 15 minus a third gives me negative a fifth. So the work done is negative a fifth joules. Okay. So that was another example using Green's theorem. Go check out the first video if you want to see another example. I'll be doing a third example before I move on to Stokes' theorem. Okay. But anyway, that's it for today's video.